titration. So when you talk of titration, this is the method that you can use to know the concentration of a known solution by using a known solution. So let's say, for example, if you have sodium hydroxide and then you're reacting with hydrochloric acid. So in this case here, let's say, for example, you know the solution of sodium hydroxide and you want to know the solution of hydrochloric acid. So this is the method that you can use. Now, so there are only 3 possible reactions that you can have. You can either have a strong acid plus a strong base, and you know to say that when you're reacting an acid plus a base, that one is a neutralization reaction. So according to neutralization reaction, what are you adding? You're adding an acid plus a base. Then what are you going to have? We are going to have a salt as well as water, which is H2O. So these are the 2 things that need to have when you react an acid plus a base. So that's just depend on what you're dealing with. It is either you're dealing with a strong acid as well as a strong base. Just depend. So the curve that I have here, it is the curve for a strong acid and a strong base. Now specifically, this is where now we are going to have the conical flask. So this is the conical flask, and in this conical flask we have acid inside the conical flask. Then you're adding a base. So this is how the graph is going to look like. So there are 2 situations here. You can either have acid inside the conical flask, then you're adding a base. So as you can see, the way the graph is starting slightly somewhere as you're here, then it continues like that. So as it is going up, there will be a point where the graph is going to, or the curve is going to be straight. So the point which I'm talking about is this point here. So this point is called the equivalence point. So this is where we are going to have the equivalence point. So when you talk of the equivalence point, it is a point at which the solution is going to be neutral. So what I mean about neutral, meaning to say that the solution is going to be either acidic or basic. So this is the point where the solution is going to be neutral. And actually, when you talk of a strong acid and a strong base, always the pH at the equivalent point is 7. So at the equivalent point, the pH is going to be 7 for a reaction between a strong acid and a strong base. So we also have another point, which is the end point. So this is where we're having the end point. So when you talk of the end point, it's a point at which now an indicator is going to change the color. The point or the pH at which an indicator is going to change its color. And approximately here we can say it is 12, somewhere 12 here. So when you talk of an indicator, what is an indicator? So an indicator is actually a substance that changes color at a certain pH. So a substance that changes color, upon reaching a certain pH. So that is an indicator. Then when you talk of an equivalent is just a point or a pH at which now the solution is going to be neutral. When you talk of an acidic, when you talk of a reaction between a strong acid and a strong base, that is the equivalent point. Now, we also have another situation where you can have the conical flask. Now this situation is now where you are going to have a base inside the conical flask. So let's say, for example, we have a base inside the conical flask and then we are adding an acid. So how is the graph going to look like? So the graph is just going to be the same but opposite. So as we can see, this is how the graph is looking like, where we are having an acid inside the conical flask and then we are adding a base. Now what about now the 1? So this is A. Now what about B? Of course it's just going to be the same one, like the way it is. But what is going to happen here is that it is going to be opposite to the original curve. So this is going to be B now. So for this one, it is the reaction of a strong acid and a strong base, but where the base is inside the conical flask and then you are adding an acid. And you need to know that the equivalent point of the pH here is 7. Then in terms of the volume is 25, approximately 25 mils. So in terms of liters, you just need to say 25 divided by 1000. Then what are we going to have? We're going to have 0.25 liters. So this is what you need to know about this one. So now, since you know what this one means, you need also to have ideas on hydrolysis. So when you talk of hydrolysis, it is with the reaction between a salt and water. So salt plus water. Then the product that you are going to have depending on the salt that you are having. Okay, so for example, if here I have, let's say, sodium chloride, then I'm reacting it with water. So what am I going to have here? I'm going to have sodium hydroxide. Then what else? I'm also going to have chloride ion plus the hydroxide ion. So this is what I'm going to have as the product. So that is one thing that you need to know on hydrolysis. Now, we also have what we call a common ion effect. So when you talk of common ion effect, common ion effect will mostly focus on the ion which is common on both compounds. Like for example, this question is saying calculate the pH of 0.3 molality of sodium fluoride solution. So the Ka value for hydrogen fluoride is 7.2 multiplied by 10 to the power negative 4. So which ion here is common? So when you look at sodium fluoride and hydrogen fluoride, the one which is common here is fluoride. So the first thing you need to talk about now, solubility. How soluble is sodium fluoride in water? So according to the dissociation of sodium fluoride, what are we going to have? Remember, this is solid. So we are going to have sodium ion plus fluoride ion. And these, there has to be in aqueous. Then what next? Remember, after talking about solubility, now you need to talk about now hydrolysis. So the hydrolysis, mostly we look at the ion which is contributing to the change in pH. So as you can see, fluoride and fluoride here is common. That's the reason why I talked about common ion effect. So sodium is not even contributing to the change in pH, but what is contributing in the change in pH is the fluoride ion. So I'm going to get fluoride ion. Remember, it is in aqueous plus water now. And water is in liquid state. Then what are we going to have? We're going to have hydrogen fluoride plus hydroxide ion, and these, there has to be in aqueous. So from there, what are we going to do? You know to say that Ka is equal to the product divided by the reactants. So according to what we have here, we can write the formula for Kw. Let me say for Ka, not Kw. So where let me just write it here. Remember, for solids and liquids we don't include them, just need to ignore them. So according to the products that we're having, we have hydrogen fluoride, we also have hydroxide ion, then on the reactant part we have fluoride ion. So this is what I'm having. So if you look at the dissociation of this sodium fluoride, according to the ratio we have 1 to 1 to 1. So this question is saying calculate the pH of 0.3 molarity of sodium fluoride. So if sodium fluoride is 0.3, even sodium ion is going to be 0.3, even fluoride ion is going to be 0.3. So even here we are going to have 0.3, but as for water we ignore it. Then here at the start of the reaction, this one is going to be 0 and this one is going to be 0. So what next? We need to write the IC table. So the IC table that we are going to have here, remember IC, ICE, I for initial, C for change, and then E for equilibrium. So what do we have? We have fluoride ion. We also have hydrogen fluoride. Then lastly, we have hydroxide ion. So this is what we have. So at the start of the reaction we have 0.3 of fluoride ion, but here 0 and then here 0. According to the reaction here, the coefficient here is 1, the coefficient here is 1, the coefficient here is 1, even here. So when the reaction is proceeding, you know what to do. For the reactant, you're going to less in terms of the change. So we have negative x according to the coefficient that you have in front of the reactant. Then for the product, you're going to add according to the coefficient. So in terms of the equilibrium, what are we going to have? We are going to have 0.3 minus x. Then here we can just say x. Then here we can just say x. So this is what we have. So Kw, or let me say Ka, is going to be equal to hydrogen fluoride. So we know to say that hydrogen fluoride here is what? According to what we have here is x. What about hydroxide ion? Yeah, hydroxide ion is also x. Then divided by. What about fluoride ion? So according to the number of, or the concentration, it is 0.3. Then our Ka, let me just write it here. So our Ka is 7.2 multiplied by 10 to the power negative 4. So we can do the multiplication there. So 7.2 exponent negative 4, then multiplied by 0.3. Okay. Then I'm going to have, so here if I multiply, I'm going to have x squared. Then here 2.16 multiplied by 10 to the power negative 4. And then I need to find the square root. So the square root of this one is going to be 1.467 multiplied by 10 to the power negative 2. That is the value of x. Meaning to say, this value of x is going to be the concentration of hydrogen fluoride as well as the concentration of hydroxide ion. So we can easily find the pOH because we have the concentration of hydroxide ion here. Remember, the question is asking us to find the pH, not pOH. So pH plus pOH is equal to 14. Then POH is equal to negative log of hydroxide ion. But for pH is equal to negative log of hydrogen ion. So we don't have hydrogen ion, so we can easily find a POH and then less it from 14. So POH is going to be equal to negative log of 1.47 multiplied by 10 to the power negative 2. So negative log of the answer. So POH is going to be 1.8. So finding the pH, I'm just going to say pH is going to be equal to 14 minus same answer which I have. Then I'm going to have 12.2 as my pH. So this is how you're supposed to answer this one. But one thing that you need to know here is that we have also this part here of identifying a salt, if it is an acidic salt, a basic salt, or a neutral salt. So when the reaction is between a strong acid and a strong base, the pH is 7, meaning to say you're going to have a neutral salt. Going to have a neutral salt. Then the reaction between a weak acid and a strong base, since the pH is greater than 7, meaning to say this one is going to be the basic salt. Then the reaction between a strong acid and a weak base, the pH is less than 7, meaning to say this is going to be an acidic salt. Then the reaction between a weak acid and a weak base, this one depends on the salt. So it just depends on, you can have a strong, you can have a neutral salt, you can have a basic salt, or you can have an acidic salt. So that is one thing that you need to know. So here we have a strong acid and a weak base. So what should you know about this one here? So for example, we have sodium hydrochloric acid plus ammonium to produce ammonium chloride. We also have nitric acid plus ammonium to produce ammonium nitrate. So according to the reaction, how is the graph going to look like? So this is how the graph is going to look like. Remember, the reaction between a strong acid and a strong base, the graph was starting somewhere 0 there, but this one is starting from 0. Let me say this one is starting from 1 and going up. And remember, what was the end point pH for a strong acid and a strong base? It was ending at 12, but this one here is ending somewhere here 9, approximately 9. But in terms of the ending point, somewhere here, which we can say it is here, where we are going to have 7.5. So the end point is less than 12. Okay. Then according to the equivalent point is somewhere here. Then you remember, for a strong acid and a strong base, the equivalent point pH was 7 for a strong acid and a strong base. Now here we have a strong acid and a weak base. And what is the equivalent point? The equivalent point here is somewhere 5.5. So 5.5 is the equivalent point, the equivalent pH for the reaction between a strong acid and a weak base. What about the volume? The volume is 25 moles. So that is one thing that you need to know. This one is just the same also. It is also talking about the same thing which I've talked about here. So in the Ka is equal to the Kb, the solution is going to be neutral and the salt is going to be a neutral. But when Ka, so Ka symbolize an acid, Kb symbolize a basic one. So if Ka, which is an acid, is greater than the Kb, the solution is going to be acidic, meaning to say even the salt is going to be an acidic salt. But when you have Kb, which is greater than Ka, the solution is going to be basic and the salt is going to be a basic one. So this reaction is a reaction where you are having an acid inside, then you are adding a base. meaning to say the opposite is going to be true when the base is inside, and then you're adding an acid. Okay, let's see the next one. So the next one is talking about the weak acid and the weak base. So you need to see the differences here. So where the graph is starting from 3. So for the strong acid and the weak base, it was starting from 1 going up. Then what was the equivalent point? The equivalent point was 5.5 pH. Now according to this one, it is starting from the pH of 3 going up, and the pH at equivalent point is 7, so it is equal to the pH of a strong acid and a strong base. But the only difference is that it is starting from the pH of 3, but for a strong acid and a strong base, it was starting from somewhere 0. Then another point is that this one is having the ending point of 8, but for the strong acid and a strong base, it was having the end point of 12. So those are the things that you need to know. Then according to the volume, it's 25 mils. So let's see in the next one. So this one can choose for the strong base and the weak acid. So for the strong base and the weak acid is this one here. Where is it? This one. So of course this one is starting from 3, like the way the weak acid and the weak base is starting from 3. Then what is the equivalent point, or the equivalent pH? The equivalent pH is somewhere 9 there, or 8.9. So we can say somewhere 8.9 as the pH, but in terms of the volume, just the same, which is 25 mils. Then in terms of the end point is somewhere here, which is 11. So those are the differences that you need to know. So now let's try to look at the questions. We have question 15, which is saying the following titration curve is the kind of curve expected for the titration of which one. So as you can see, this one is starting slightly somewhere 0 here, as you can see, and the equivalent point here is 7. So what curve is this one? Is it for the strong acid and the strong base, or a strong acid and the weak base, or a weak base and a weak acid, or a strong base and a weak acid? So according to what we have here, this one is going to be a strong acid and a strong base. Okay, so that is the answer. Then this one, I think we talked about this one, whose definition of acid and base emphasize the law of protons. So which one is this one? So when you talk of Arrhenius, it emphasizes on an acid as a proton donor and a base as a proton acceptor. And then Blosted and Lowry mostly, let me say this one focuses, Arrhenius focuses on a solution which is having the acid having more hydrogen ions and a base having more hydroxide ions. Then Blosted and Lowry emphasize on an acid being a proton donor and a base being a proton acceptor. So since here we're talking about the protons, meaning to say the answer is going to be this one, but for the Lewis theory, this one emphasizes on the pair of electron. Then the next one, the pH of the solution is 4.3. What is the correct hydroxide ion and the condition of the solution? Wow. So what are we going to do here? We need to find the hydroxide ion. So we know to say that pH plus pOH is equal to 14. So we can find pOH, 14 minus 4.3. So what are we going to have? 14 minus 4.3. So I'm going to get 9.7. So pOH is 9.7. So we know to say that pOH is equal to negative log of hydroxide ions. Then here I can divide by -1, even here by -1. Okay, so what are we going to have? We're going to have log hydroxide ion, and this is going to be equal to negative POH. So we can express this one in exponential form, where we're going to say this one is going to be the hydroxide ion. The hydroxide ion, which is going to be equal to 10 to the power negative POH. So what is our POH? So negative to the power 10 to the power negative 9.7. Okay, so 10 to the power exponent negative 9.7. So here I'm going to have 1.995 multiplied by 10 to the power negative 10. Okay, so to round off this one, you can just say this is 2.0 multiplied by 10 to the power negative 10. So according to this solution, what can we say about this solution? So most of the times hydroxide, this one focuses on bases, and we know to say that bases, they have a pH greater than what? Greater than 7. So greater than 7, that is the base. Then for hydroxide, this focuses mostly on acids. So since we're talking about hydroxide, meaning to say this one is going to be base, and we know to say that base is basic. So meaning to say our answer is just going to be D. Then this one, the titration curve is for which one? So it's sending on 12, but remember this one is the reverse one, where, if you remember, you have acid, then you're adding a base. This one is the first one, and it was looking something like this. But when you have a base inside, then you're adding an acid, it has to look something like this. So that is what we're having. So we're adding an acid, we're titrating an acid. So of course this is the reaction between a strong base and a strong acid. So we have two things, C and A. So which one here? Is it the titration of a strong acid with a strong base titrant, or the titration of a strong acid and a strong base with a strong acid titrant? So a titrant, if you remember very well, a titrant is a solution whose concentration is known. So when something is inside now, when something is inside the beaker, meaning to say you know the volume, you know the concentration. So you can choose from here which one is the answer. Is it A or C? I've told you about that one, so you can just choose. Then question 8b, define a Lewis acid. So when you talk of a Lewis acid, let me start with Arrhenius. Arrhenius theory mostly focuses on a solution. When you talk of an acid is a solution with more. An acid is a solution with more protons, or let me just say hydrogens. That is an acid. Then when you talk of a base is a solution with more hydroxide. Then when it comes to blostetanol, this one focuses on the proton. Okay, protons. So an acid is a proton donor. Then when you talk of a base, so let me say proton donor. Then when you talk of a base is a proton acceptor. So you can say proton acceptor. Then when you talk of Arrhenius, let me say when you talk of Lewis focuses on electron pair. So since acids here, they are donating protons, when it comes to Lewis, acids are going to be any solution which is going to accept a pair of electrons. So we're going to say acid solutions that accept a pair of electrons. So we are going to say electron pair acceptor. Electron pair acceptor. Meaning to say they are able to accept electrons. They're not about acids. So when it comes to acids, let me say when it comes to bases, these are electron pair donor. Electron pair donor. So since it is talking about an acid, go with this one here, a solution with that accept electron pair. And then we have this question here, which is saying hypodious acid, which is this one here, has an acidic ionization constant of 2.5 multiplied by 10 to the power negative 9 at 25 degrees Celsius. What is the hydronium ion concentration in 0.5 molarity of this solution here? Okay, so what are we going to do here? So let me just use this part here. So remember, this question is focusing on an acid, meaning we are focusing on Ka. We are focusing on Ka. So Ka, we have the acidic ionization constant here, which is 2.5 multiplied by 10 to the power negative 9. So if this one here undergoes ionization or ionic equation of this one here, what are we going to have? Okay, let me do this. What are we going to have on this one? We are going to have iodide plus the hydroxide ions. So this is what we are going to have. So in terms of Ka, we have the product, which is iodide, also have hydroxide ions, then divided by this acid here. So if we write the IC table here, what are we going to have? So for the first part we have the acid, in the second part we have iodine ion, also have hydroxide ion. So at the start, this question is saying we have this concentration of an acid. Okay, so the concentration of an acid here is 0.64. Then at the start here we are going to have 0. So according to the ionic equation here, the coefficient that we have 1, 1, 1. So here we're going to less, let me say, not like this. Okay, let me just do this. I'll have this one and this one, so that I say this one is going to be initial, this one is going to be change, and this is going to be the equilibrium. So we are going to say minus x and then plus x plus x. Then what are we going to have? We are going to have 0.64 minus x and then ax and then ax. So according to the Ka that we have, our Ka is 2.5. So I can write it here. So we have 2.5 multiplied by 10 to the power negative 9, which is going to be equal to the concentration of this one here. What's the concentration of this one? That is x. And then for hydroxide, that is x also. Okay. Then from there, what are we going to do? We have the concentration of an acid here, which is what's the concentration? 0.64 minus x. So here we can just say we need to assume that this x here is less than 0.64. So if we assume that x is less than 0.64, meaning to say this one we are going to ignore it. If we ignore it, meaning to say we are going to discard it. The reason is just very simple. If we assume that that one is less than 0.64, meaning to say it is not going to even cause any effect when we do the calculations here. So x multiplied by x, that is x squared. Then what are we going to have? Okay, so what are we going to have? So let me just do the multiplication here. Exponent negatives, then multiply by 0.64. So here I'm having 1.6 multiplied by 10 to the power negative 9. Then the root of that, the value of x is going to be equal to 4.0 multiplied by 10 to the power 5. So this is going to be the concentration of iodide ion as well as the concentration of hydroxide ion. So remember, we are finding the concentration of hydronium ion. Okay, the concentration of hydronium ion. So let's do this. We know to say that Kw is equal to Ka multiplied by Kb. Also Kw is equal to the hydronium ion multiplied by the hydroxide ion. So from here we know to say that we have known the concentration of hydroxide ion, and we want to find the concentration of hydronium ion, and we know to say that the value of Kw at 25 degrees is 1.0 multiplied by 10 to the power negative 14. So it's just going to be very easy for us to calculate this one. So Kw is 1.0 multiplied by 10 to the power negative 14, which is going to be equal to hydronium ion. Then the concentration of hydroxide ion we have calculated, which is 4.0 multiplied by 10 to the power negative 5. So the concentration of hydronium ion is going to be equal to 1 exponent negative 14, then divided by 4 exponent negative 5. So the answer which I'm getting is 2.5 multiplied by 10 to the power negative 10. So this is my answer. Okay, then the next one is saying predict whether an aqueous solution of aluminium sulfate, where the Ka for hydrated aluminium is this one and Kw is this one, for the Ka of sulfuric acid is 1.24, let me say 1.2 multiplied by 10 to the power negative 4, will be acidic, basic, or neutral. So what are we supposed to do here? So here we need to find Kw and then compare with Kb. So we have been given Kw, let me say we need to find Kb, then we compare it with Ka. So we need to say that Kw is equal to Ka multiplied by Kb. So Kw we know to say is 1.0 multiplied by 10 to the power negative 14. This is going to be equal to Ka. We have been given the Kb for hydrated aluminium as well as the Kb for sulfuric acid. Which one is contributing here more? So the lower the number, so if I say which one is more acidic, which one is more acidic between 2 and 4. So in terms of the acidity of something, the lesser the value, the more the acidic something is. So which one is less between the Ka for hydrated the hydrated aluminium ion as well as sulfuric acid? Between this one here and this one, which one is smallest? So this one here is bigger than this one in terms of the values. So we have 1.2 multiplied by 10 to the power negative 4. We also have 1.4 multiplied by 10 to the power negative 5. So this one is the smallest, meaning to say this is acidic than this one. So the one which is contributing to the acidity is this one here, which is hydrated aluminium ion. Is the one which is contributing. So meaning to say this is basic and this is acidic. Of course, both are acidic, but which one here is more acidic? So I'm going to use now the Ka for this one. So Kw we know to say is 1.0 multiplied by 10 to the power negative 14, which is going to be equal to Ka. I'm going to use this one, then multiply by Kb. Okay. So in terms of the value, what is going to be our Kb? So here I'm going to get 7.1 multiplied by 10 to the power negative 10. This is my value for Kb. So if I compare this one and this one, of course this one is the smallest, but when it comes to the basicity of something, the smaller the value, the smaller the pH, isn't it? So if you compare this one and this one, which one is more powerful between this one and this one? Of course, when it comes to acidity, it's the opposite. If we had a solution for the Kb, which was like, let's say 1.5 multiplied by 10 to the power, let's say negative 4, this one here is bigger than this one. Now that this one is smaller than this one, meaning to say the solution is going to be acidic. Here what you need to know is just to know how to manipulate these values in terms of when the value is small, in terms of the acidity. Is it going to be more acidic or neutral? Or it's going to be basic? And when the value is very big, when it comes to the basicity, is it going to be basic or acidic? So that is one thing that we need to know. So the conclusion here is to say this one is going to be acidic. The next one, calculate the molar solubility of we have lead chloride in 0.2 molarity of lead nitrate solution. So given that the KSP for lead to chloride is 1.7 multiplied by 10 to the power negative 5. So we are going to consider the ion effect. So first let me just write the ion effect of this one, or the decomposition of this one, or the ionic equation of this one. So according to what we have here, when this one dissociates, what are we going to have? We're going to have 2 molarity of lead 2. Let me remove 2 here. It has to be like this, lead 2. Then multiply by, since here we have 2 moles, so I need to put 2, then nitrate, then a negative there. So this is what we have. So in terms of the ratio, we have 1 to 1 to 2. So if lead 2 nitrate is having 0.2, even lead ion or lead 2 ion is going to have 0.2, but this one is going to be 2 multiplied by 0.2. That is one thing that you need to know. So when you talk of a common ion effect, I'm looking at the ion which is common here. As you can see, lead is common here, even here lead is common. So we have this value here for lead. So now let's focus on this one, since It's the one that they have given us, the KSP. So let's also write the dissociation of this one. So the dissociation of this one, what are we going to lead to? Then plus, since we have 2 atoms, so I'm going to say 2 moles of chloride ion. So from there, we know to say that here we don't know, this is solid, this is aqueous, and this is also aqueous. But one thing that you need to know to say that we also know the concentration of lead. Since this one is lead and this one is lead, so they are going to have the same concentration, which is 0.2. We have lead to ion. We also have chloride ion to the power 2. Remember, the power is the coefficient. So according to the ionic equation that we had this one here, which is giving us lead plus 2 moles of chloride ion. So this 2 here, it is also part of our reaction here. But remember, the concentration of lead to ion is this one here, according to the analysis. So we are finding KSP. Let me say we're not finding, we are finding the, given that the KSP of lead to chloride is that one, so we already have KSP. So what are we going to have? KSP here is 1.7 multiplied by 10 to the power negative 5, which is going to be equal to, here is 0.2 plus S if we want, but S is just going to be ignored here. Can just assume that it is less than 0.2. Then here I'm going to say, since we don't have the concentration of chloride, so I'm going to say 2. This 2 is coming from the coefficient that we have here. Then S for solubility, then to the power 2. So this 2 is the power. From there, what are we going to have? We are going to have 1.7 multiplied by 10 to the power negative 5, which is going to be equal to 0.2. So let me just write 0.2 here, because it's more like I'm dividing. Even here. So what am I going to have if I divide that one? Okay, so before I divide, what else can we do here? We can multiply. So 2 to the power 2 is 4. And then S to the power 2 is S to the power 2. So 4 multiplied by 0.2 is 0.8. So I can divide by 0.8 here. Even here. So these are going to cancel each other. So S squared is going to be equal to, so when I divide, I'm going to get 2.125 multiplied by 10 to the power negative 5. Then the root. So S is going to be equal to 4.6 multiplied by 10 to the power negative 3 moles per liter. So that is what we are going to have as our final answer.